Hey guys, how's it going? So today we're going to talk about constitutional isomers. So constitutional isomer basically means any structure that um, has different connectivity but the same molecular formula. So that might have sounded like a bunch of gibberish to you, but essentially just consider the molecular formula of, say, this right here, right? So right here you see a CH3 group, okay? So you got like a CH group right there. You got another CH3 group right there. You got a CH2 right there. You got another CH2 right there. You got another CH2 right there. And then you got a CH3. So essentially, the amount of carbons that you have in this and the amount of hydrogens have to add up in the other a constitutional isomer of it would have to have the same number of carbons and the same number of hydrogens, essentially, but the only difference is that it would have to have different connectivity. So in this case, we're going to, first of all, let's number the carbons. Okay, so you're going to look for the longest chain. You can either start from the left or the right. The reason we're going to start from the left is because we want the number where the carbon, where it's attached to something, we call it a substituent. We want it to be on the lowest number. So if we started from the left and we started numbering 1, 2, 3, this would be number 5. Whereas if we start from the left, it's number 2. Do you see what I mean? So we want it to be, the substituent to be on the lowest number. Let's keep naming our carbons. Okay, this is our longest chain right here, and it's 6. Okay, another way you could actually go about it is 1. Now, keep in mind this would come out to the exact same answer, so it doesn't really matter, but it's 1, 2, 3, 4, 5, 6. Do you see what I mean? So that could be another carbon chain, and you could consider that as your methyl group. Anyways, so now looking at a constitutional isomer, basically what you want to do is you want to have different connectivity. Essentially what that means is, if I were to go ahead and draw this is not a constitutional isomer. And you might be wondering, well, boss, how is this not a constitutional isomer? Because remember, now you have to start from the right. You can't count from the left again because you want when you're counting carbons, you want to count it from a side where the substituent would be at the lowest number. So if we start from there, again, it would be number 5. But if we start from the right, it would be number 2. So 1, 2, 3, 4, 5, 6. This is not a constitutional isomer because the methyl group is still coming off the 2 just as it was right here. This is not a constitutional isomer. It's just this flipped around is essentially what it is. A constitutional isomer basically means that you have the same formula, but you have this methyl group or whatever attached somewhere else. So you can either attach it, I don't know, if we attached it here, that would be allowed. Because now it would be on 1, 2, 3. Now it would be on the third carbon, right? Or for example, 1, 2, 3, 4, 5, 6. Yeah, okay. So that would be on the third one. Either way you go. Or another way you could think about it, if you wanted to go about it, is that would be on 1, 2, 3. Yeah. Anyways, another way you could do it is you could do this. That's another constitutional isomer. So now you might be thinking, well, boss, how am I supposed to know how many carbons and hydrogens there are without drawing it in every single time? Well, essentially, the saturation, this is something you haven't learned yet, so don't worry about what saturation is quite yet. But essentially the point is that unless there's a double bond somewhere, or unless it's a ring, we don't need to worry about where we draw this in. No matter where we draw it in, the carbons and the hydrogens will add up. So it won't actually matter in the grand scheme of things. So in this example, if we do want to count it up, for example, okay, we got CH3, CH2, 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 I think of CH3, CH2, 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 and a CH3. Let me make sure I did that right. CH3, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Yep, okay. So now let's count up the carbons. 1, 2, 3, 4, 5, 6, 7. 7 carbons. How many do we have here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. So the carbons do match on both of them. Okay. The hydrogens, we have 3, 5, 7, 9, 11, 13, 16. 16 hydrogens. And on this one we have 3, 6, 7, 9, 11, 13, and 16. So 16 hydrogens right there as well. So once again, you see how the molecular formula is the exact same. The same number of carbons, the same number of hydrogens. The only difference was, instead of having this come off of the 2 now, instead we just added it towards the end. So now the carbon chain is 7 long. Do you see what I mean? Sorry. And another way to do this would be, you literally just take for example, whatever group, and you just move it wherever you want to. So we could technically move it over here if we wanted to, or we can move it to over here if we wanted to. The only thing is, you can't move it to somewhere that would be the same as this. So for example, like I showed you guys earlier, this would not count as a constitutional isomer because you're moving it to a spot where it's still, the connectivity is still on carbon number 2. So if you guys understood that.